This video is brought to you by PPL Europe, a not-for-profit community of European general aviation pilots dedicated to helping ourselves and others to use our licenses to the full. We share our passion for flying through mutual exchange of expertise, experience, information, inspiration, and education. We also assist regulators in framing legislation that affects all GA pilots. We're almost all volunteers and do it because we love it, though we do also need to raise a little money, mainly to fund our representation and lobby activities. Please join us, improve and broaden your own flying, enjoy belonging to a community of like-minded pilots, and help us represent you. Hi, this is the fifth in the series of instrument flying videos I'm making for PPL Europe. They're aimed primarily at European IFR GA pilots, but a fair deal of the stuff here is applicable to non-European and VFR pilots. In this video, I'm going to focus on RNAV, RNP, and PBN as they apply to the GA pilot. I know that I've started by using three very confusable terms caused by a gradual development history during which rules and regulations have struggled to keep up with technology in different administrations. Particularly FAA and EASA have struggled to agree and keep pace with one another. But I'll try to cast some light on the bits you need to know and reassure you about the bits you don't. PPL Europe produced a book on the subject, the PBN manual, of which I'm one of the authors, and is available from the PPL Europe website. So I, of course, recommend it, but I'll try to cover the highlights. The first half of this video is going to be about theory and definition. I'm really sorry about that, and I've thought about it long and hard, but I really think you need some of the basic theory or you won't understand some of what you see when it comes to the practical stuff. So let's start with some definitions. Boring, I know, but in a world dominated by acronyms, we need to be on the same page. Let's start with RNAV, or area navigation. This is simply a way of navigating a route without having to go from terrestrial radio beacon to terrestrial radio beacon. The early examples were inertial navigation, whereby the aircraft knows where it is by dint of remembering all the accelerations the aircraft has been subject to, and VOR DME shifters, whereby you can navigate to a position directly based on its and your radial and distance from a VOR. Later examples include DME, which can fix your position providing there are no errors in the system, and DME, which is similar but more failure resilient, and DME IRU, which uses inertial navigation corrected by DME. But the only RNAV system that most of us in the Cessna 172 to Navajo range that I've been discussing in all these videos will ever see will be satellite-based. So, what satellite-based systems are there? Well, the best known is the US government's GPS system, and for years that was the only game in town. However, there are now quite a few satellite constellations out there. The Russian GLONASS, the European Galileo, Chinese Beidou, as well as localized Japanese and Indian systems. These systems are collectively known as Global Navigation Satellite Systems, or GNSS for short. So GPS is just one example of a GNSS system. To refer to them all as GPS is rather like vacuum cleaners all being dubbed Hoovers. We probably all know that approaches using satellite systems were initially called GPS approaches. Then, as it became clear that other satellite systems could be used, GNSS approaches. Then came the realization that other non-satellite-based RNAV systems could theoretically be used. They were called RNAV approaches, which is mostly where they sit as I make this video. But increasingly, they're being designated RNP, and ICAO has decreed that by the end of 2020, all such approaches will be RNP approaches. So what is RNP? RNP, Required Navigation Performance, is simply an RNAV specification that has onboard monitoring and alerting. That means a mechanism for alerting the pilot when something is in the system has failed or is not performing to an acceptable standard. Because RNAV approaches all require onboard monitoring and alerting, and always have, they have, in reality, always been RNP approaches. So this latest change in name is only really catching up with reality and naming them as they should always have been named. There are also RMP-AR approaches, which require even higher level of fault tolerance and recovery, but they're not available in the aircraft types we're discussing, so I'll leave them with only a passing mention. So GPS is a type of GNSS, but there are other GNSSs, and GNSS is one way of achieving RNAV, but there are others. RNAV is enhanced by onboard monitoring to be called RNP, and RNAV and RNP form the navigational backbone of PBN, but there are many other components of the PBN system. So that leaves just one more acronym, PBN, Performance-Based Navigation. Well, PBN is a description of everything that has to be combined to make navigation and approaches work. RNAV and RMP cover the aspects that make aircraft follow particular magenta lines in space, but PBN encompasses everything else as well, such as procedure design, air traffic management, database provision, pilot and controller training, in fact, the whole environment. So it's not surprising that people get confused by these 5 terms, especially as each term has come to be replaced and enhanced by its predecessor. I know I'm using a lot of acronyms and will probably be introducing more, and probably then rattling them off later. So I've made a list with brief explanations in the comments below. So if you get overwhelmed, you can put me on pause and refer to them. PBN underpins much of the en route and terminal procedures, such as SIDS and STARS, and a purist would say that you should really know the performance specification of every leg you fly, whether it's RNAV, RMP, and to what precision. But in reality, it's difficult to discover that information without digging deep in the manuals, and it's pretty useless information. You just fly the magenta line and keep the CDI in the middle, and you'll be fine. But where you really do need to know the nature of the leg you're following is on the final approach. But that is made very easy for you because it is enunciated by your GNSS navigator, and for glass pilots, also shown on the PFD. There are 5 different enunciations that pilots might see in Europe: APR, LNAV, LNAV plus V, LVNAV, and LPV. These enunciations are the result of the more limiting of 2 things: the precision of the designed approach and the quality of the signal being received. Let's start with the best of circumstances, LPV. That means you have approximately the same precision and reliability as the ILS, and that both the approach design and the satellite signal support that. The needles on the HSI or OBS will behave indistinguishably from the ILS, though experience tells us they're actually a little more stable, down to minima as low as Cat 1 ILS, i.e. 200 feet and 550 meters RVR. Nearly, but not quite, all recent and planned approaches are LPV. However, you could be flying what is designed as an LPV approach at a time when the satellite signal is not good enough, either because of satellite geometry or failure, but is good enough for a lesser approach. That lesser approach will then enunciate, and you must fly to the appropriate minima. So, to labour the point, if you're expecting an LPV approach with a 200-foot decision height and a 550-meter RVR, but the enunciator says LNAV, then you must use LNAV minima, which might be, say, 400 feet and 1,500 meters RVR. There is another rule in Europe which says that you can only accept that change when you're higher than 1,000 feet above the airport. So if the enunciator initially says LPV, then changes to LNAV, you must check whether you're above 1,000 feet. If you are, use the LNAV technique and minima. Otherwise, go around and have another go using the higher minima. These changes in enunciation are rare, but not unknown. They are most likely in mountainous terrain and near the edges of coverage of the SBAS satellite, which I'll be talking about shortly. You can see how, as we're talking about fringe coverage and terrain effects, the enunciation might change as you descend. So that's the LPV, the preferred approach and increasingly the most common. I'm now going to jump to the oldest and original approaches, which are referred to in plates as LNAV for lateral navigation, but which older GNSS navigators, such as the GNS 430, i.e. the one without the W at the end, enunciate as APR. The reasons for this are fairly obvious. When the GNS 430 and earlier boxes were designed, this was the only approach, so it could be safely labeled approach. It's only when boxes capable of more sophisticated approaches came along that they had to distinguish. So, if you see APR in an old box, you may be flying an LNAV approach, but more likely you're flying an LPV, but your box is incapable of recognizing that, so it behaves as if it were an LNAV approach. Either way, you must use LNAV minima and check altitudes. Now we move on to a bit of a complexity, so put your thinking hat on and listen carefully. Early boxes, such as the GNS 430 and their equivalents, many of which are still in use both in GA aircraft and in airliners, did not represent the final approach track with increasing sensitivity, as you see in all other approaches from NDB and VOR to ILS, but as a fixed distance either side of the track, with a full-scale deflection sensitivity of 1/3 of a nautical mile. It's easy to see that that reduces the precision with which you are positioned at the decision point. If you have half-scale deflection, the maximum acceptable without going round, you are 275 meters off to one side, which is 8 or 9 degrees, depending on the decision height, making visual acquisition of the approach lights less likely. Newer boxes, such as the GNS 430W, GTN, and IFD, enunciate LNAV and no longer use that tram track precision, but use increasing sensitivity as the aircraft gets closer. But the approach designer has to work on the assumption that aircraft are using the tram lines and design their minima accordingly. So, I've now talked about LPV, LNAV, and APR. The other two are hybrids and a little more complicated to describe. Firstly, LNAV plus V. Almost any LNAV approach you fly on a newer navigator from the GNS 430W onwards will actually enunciate LNAV plus V, and a glide path will be shown. However, that glide path is not part of the published procedure. It is added by Garmin or Avidyne to make your life simpler. You still need to treat the approach as non-precision and check your altitude every mile. But the advisory glide path indication should take you from check altitude to check altitude on a stable descent. But it's not an official glide path, and it shouldn't be treated as such. It has no more validity than, for example, the so-called ILS approach feature in SkyDemon. It also creates something of a dilemma when the temperature is significantly different from ISA, because although the plus V glide path still traces the same line in space regardless of temperature, the altimeter is affected by temperature and will show you lower than you actually are in hot weather and higher than reality in cold weather. That means that if you follow the unapproved glide path, your check altitudes will be wrong. And if you use check altitudes, the glide path will show fly down in hot weather and fly up in cold weather. So, do you trust the uncertified but more correct glide path, or do you follow the certified but inaccurate altimeter? A type of dilemma that's been with us a long time in aviation, at its most salient when choosing between approved ADF and the unapproved magenta line on an NDB approach. My advice is to follow the electronic glide path in real life, but the check altitudes on test. Finally, the LNAV-VNAV approach, enunciated as LVNAV on your display. As far as pure GNSS users are concerned, this is a sort of historical anomaly based on how airliners fly. They mostly have a vertical guidance system called baro-VNAV, which presents a glide path derived from barometry. Based on the QNH and temperature, it knows the expected pressure at any point on the final approach path and can indicate deviation from that expected pressure through the normal glide path indicator. When LNAV approaches were first in use in the 1990s, giving only lateral guidance, baro-VNAV was added to provide vertical guidance. But most light aircraft do not have baro-VNAV. The only light piston aircraft I've flown that has it is some later models of Cirrus. So, to allow GNSS users to fly LNAV baro-VNAV approaches, the LNAV-VNAV approach was developed. This uses vertical guidance purely from the GNSS to produce a glide path without baro-VNAV. In terms of design, although all GNSS users get lateral guidance with increasing sensitivity, airliners using baro-VNAV may still be getting tramline sensitivity. So the minima, again, are higher than for the LPV, even though the actual performance of the GNSS box is just about the same. I know it's complicated, but you really ought to know. The bottom line is, if you see APR, LNAV or LNAV plus V, it's a non-precision approach, but LNAV plus V helps you fly the glide path. If it's LVNAV or LPV, it's a fully certified approach that you can use to minima, like an ILS. Now, let's talk about SBAS. SBAS is what enables the GNSS navigator to show a glide path. It compensates for the fact that vertical precision is rather poor using raw GNSS. It's available in GNS 430W and 530W, G175, GTN, IFD, and in some later G1000s. It's what distinguishes the GNS 430W from the GNS 430. The GNS 430 does not have this feature. There's more naming confusion here because different parts of the world have different SBAS systems, and some have none. In the USA, SBAS is called WAS. WAS is why there is a W on the end of GNS 430W, and that confuses many people into thinking that there's a WAS in Europe. But European SBAS is called EGNOS. I'll describe in a moment exactly how SBAS works, but the important thing to know is that while each GNSS constellation has between 20 and 30 satellites covering the whole world, each SBAS system, such as WAS and EGNOS, only has one active geostationary satellite operational with a spare backup in case of technical problems. A geostationary satellite can only sit above the equator. That in turn means that SBAS is more difficult to deliver to the Arctic. EGNOS coverage seems to vary considerably on a daily basis. I'm not sure why, but I'm sure someone will tell me in the comments. But it's only really at its most available in an area bounded by Faroe, the Faroes, Trondheim, Helsinki, Ankara, and Naples, with the north of Scandinavia, including most of Finland, Sicily, and eastern Iceland getting slightly less reliability, and in Reykjavik and Murmansk, it not being very reliable at all. SBAS has a network of ground stations called RIMS. To give you an idea, there is approximately 1 RIMS per country of Europe. There are 2 in the bigger countries, like France, Spain, and the UK, but none in Benelux, so it sort of averages out. There are also RIMS on the periphery, in Africa, Jan Mayen, Svalbard, and Turkey, to give wider coverage. Each of these RIMS knows exactly where it is, to the millimeter, horizontally and vertically. So, when it picks up a GNS signal, it knows exactly how wrong the signal is. The error signals from all the RIMS in Europe are integrated and calculated, and the resulting correction is sent up to the geostationary satellite so that it can be rebroadcast to aircraft. So, for the sake of argument, let's say that the RIMS in Toulouse gets a GNSS position that's wrong by 2 meters northeast horizontally and 2 meters vertically, and the one in Paris is wrong by, say, 1 meter west and 4 meters vertically. Those errors are processed and sent to the satellite. Then an aircraft flying an approach in, say, Limoges might get an instruction from the satellite to shift its display position southeast 1 meter and 3 meters down. This is, of course, a massive simplification, but it should help you picture what's going on and what SBAS is doing for you. Essentially, it makes your position, most importantly your vertical position, much more accurate. We now need to talk a little about alerts and messages. On the GNS, a loss of integrity enunciates as an INTEG flag. On the GTN and G1000, it's LOI for loss of integrity. On the IFD, there's a variety of more specific messages announcing what facilities are unavailable. The theory behind alert levels and time to alert is quite complex, and we won't go into it here. But it has been worked out by people cleverer than us, and the bottom line is that if you get an integrity warning, the navigator is no longer providing the guidance you were expecting. It might mean that an LPV has been degraded to LNAV, or it might mean that you're getting no usable satellite signal. But any which way, it cannot be ignored, and it may mean that you have to revert to legacy navigation such as ILS, ATC radar, or VORDME. The other thing that must not be ignored is the message annunciator. When you press on the message button, you might see something that's vital, but it's not all that obvious on the GNS, and even less so on the GTN. The redeeming feature is that the GTN and IFD will throw up important messages on the screen. But nonetheless, the message button should be in your scan and you should not ignore it. One bit of theory I'm not going to talk much about, though it's important to regulators and designers, is the different RNAV and RMP specifications like RNAV5 and RMP1. They play little part in how you fly, and you can read about them in the PBN manual. The bottom line is that you should keep the CDI in the middle, and it's more sensitive the closer you get to the threshold. The sensitivity doubles when you're closer than 30 nautical miles to the destination, and then increases on final approach. That's about it, really. Is that enough theory? Sorry about having to do that, but it's all stuff that you do need to know if you're going to use the equipment safely, especially when stuff starts to go wrong. Let's now get a bit practical and go through a fully PBN flight with a SID, an en route segment, a star, and an RMP approach. Firstly, a fundamental concept which is blindingly obvious, but which underlies quite a lot of issues people have with navigators. The FPL, or flight plan, is a sequence of waypoints, and the navigator will always step through that sequence from top to bottom, regardless of the stupidity of doing so, unless it's suspended, which happens in holds at the missed approach point, or if the next requirement cannot be computed. But the main point is that the sequence in the flight plan is what it will fly, even if that results in a bizarre trombone. Another point that people sometimes miss is that an approach is nothing more than a series of flight plan legs, each with their own characteristics and precision. The intermediate and final segments are coded to the level of precision required by the approach, so LNAV or LPV, and the final segment also supports a glide path, but they're still just legs. The missed approach procedure is also just a series of legs, the first of which is very often a climb to altitude leg, which means that it doesn't terminate at a waypoint and sequence to the next, but when the aircraft reaches the designated altitude. However, there's a special case when the aircraft reaches the missed approach point, regardless of whether it lands or has gone around, where sequencing is suspended. The navigator will simply point you straight ahead forever, or until you press the unsuspend button to continue sequencing. I'll be talking a bit more about this in a minute. Holds also place you in suspend mode. Before you can use your GNSS navigator for flight in PBN airspace, you must check that the navigation database is current. This appears on the opening page when you start up. Do not just skip over it, but check it every time. The database is updated every 28 days on the AIRAC cycle, so you must update your GNSS before the next flight after the AIRAC day. You are permitted to fly with a database that's up to 28 days out of date, but only if you check every element of it you intend to use against up-to-date reference material, so it's not really practical. Also, if you're intending to use an approach on an old pre-SBAS unit, such as the GNS 430, you must check that adequate satellite coverage is predicted for the approach at the time by using RAIM, either online or on the box. Let's start with how you get the routing into the GNSS system. You can just do it manually, which on newer navigators like the GTN and IFD isn't too painful, as you can put in airways and it inserts all the waypoints on the way. But on older boxes, such as the GNS and G1000, it's a real pain. The pain really comes home to you when you have spent 10 or more minutes putting in tens of waypoints, then shortly after departure, you're either vectored or given a direct to the 15th waypoint on the list. A convenient way to get the route into the GTN without any external equipment is to write it directly from your planning application, such as AutoRouter, onto an SD card. It needs to be in a directory called FPL, directly off the route of the card. Then you can take that to the aircraft and copy it into the catalogue. A third way is to have the route on your tablet, either because it's been generated there by, for example, ForeFlight, or because you've copied it into, say, Garmin Pilot from AutoRouter, and then to write it directly into the GNSS by Wi-Fi or Bluetooth. This is handled natively by the IFD, but Garmin boxes need an extra interface called FlightStream, which has to be behind the panel for the GNS, but cleverly is built into an SD card for the GTN. If you fly with ForeFlight or Garmin Pilot, You can then make changes to the route, either on the iPad or in the navigator, and it will cross-fill to the other. So your iPad is integrated into your panel. However you got the route into the navigator, be sure to, at the very least, zoom right out of the map and make sure that the route makes sense. I've had a route that went from Germany to France via the Marshall Islands in the Pacific because Garmin Pilot failed to differentiate between a 2-letter NDB overlay waypoint in Belgium with one of the same name there. It was surprising to see that the plan said I was going to arrive with minus 14,000 litres of fuel, which did rather give the game away. But nonetheless, it's really important to check that the picture looks right. So, one way or another, we're now on the ramp with the planned route loaded, and at some point we get our actual clearance. The routing engine didn't know which runway would be in use when it created its route, so it's very common to have to change the SID. This is luckily very easily achieved in a few keystrokes or touches, but equally, it's important again to have a look at the map and check it still makes sense. Does it fly you 50 miles to the west, then bring you back 20 miles to the east? Because the next point after the end of the SID made sense with the original SID, but not with the new one. Something that happens thankfully rarely is that you are given a clearance completely different to the one you've planned. It happens mostly if you tried to buck the system with directs and lat long or displaced waypoints. If your clearance is different, you need to enter it, but also replan fuel and potentially weather. So it's a real pain when it happens, and a good argument for not trying to be too clever about the routing. My advice is to accept a Eurocontrol routing and follow all the vectors and directs, which will shorten it anyway. Before you take off and fly the SID, have a good look at the plate in JEP or the AIP. Don't just rely on the magenta line. Often there's a note telling you to change frequency immediately after takeoff, especially in Germany. Listen out for the hint, clear takeoff and have a nice flight. And many navigators don't give the vertical constraints. Remember that if you're cleared for a departure but not given an altitude or level, then you must fly the constraints on the chart. In some software versions of some navigators, such as recently updated GTNs, they are provided, but not in GNS or older G1000s. There may also be climb gradient limitations, and pilots of multis need to think about whether their one engine in operative climb performance is adequate to meet them. There's no point in doing a beautifully executed IFATO and then, just when you're congratulating yourself, smacking into the side of a mountain. Once you're on airways, you're almost certainly in PBN airspace, and there's therefore no need to tune in VOR DMEs. Some people like the belt and braces approach, and there's certainly no harm, especially if you have little to do. I have to say that it never occurs to me to do so. If your autopilot has GPSS or roll steering, those are two words for the same thing, then you can just leave it engaged and it will treat airways waypoints as flyby, which they invariably are. But if not, you may need to disengage nav mode and use the heading bug to fly by each waypoint. If you don't, your autopilot will treat all waypoints as flyover, which is against the rules, potentially disruptive, time-consuming, and uncomfortable. You'll almost certainly get directs from ATC. As soon as I hear my call sign, I hit FPL on the navigator. Did you know that if you touch the magenta waypoint on the GTM map, it takes you there? So I'm ready to search my plan for the foreign accented waypoint name. If they say what you hear as direct Piram, and there's a peron in the plan, that's almost certainly what they mean, and you can read it back with confidence and select direct. If there isn't a matching waypoint, note what you think they said and read it back imitating them. Then look ahead on the chart for likely candidates. If you can't find it in, say, 10 seconds, then call back for a spelling. Don't be embarrassed, airline pilots do it all the time. Your GNSS equipment will almost certainly provide you a mechanism for determining top of descent. In older navigators, it needs to be set up by the pilot each time and only gives you your required rate of descent from your present position. In newer ones, a top of descent marker is added automatically, as well as an arc to show where you will meet your target altitude. Use these tools to communicate with ATC. They're not used to non-pressurized aircraft and may not offer you a descent until you are much too close in, risking your passengers' eardrums. So, initiate your top of descent by about 2 minutes and ask for it, so that they get back to you in time for you to initiate descent just when you want to. Get the ATIS early so you can anticipate what approach is in use. Your GNSS navigator will have both RNAV, RMP and overlay approaches, and you should get used to setting up the overlays as a backup. Generally, across Europe as a whole, RNAV, RMP approaches have higher minima than ILS. So if the cloud base is very low, it's obviously wiser to use the ILS. But if the cloud base is well above the RNAV minima, as it generally is, then it is lower workload to use that, as in most installations there are fewer buttons to press and less chance of missing something, most commonly the CDI switch. So I generally ask for the RNAV or RMP approach if I can. Use the cake slices on the chart to determine which initial approach fix you're going to use. The IAFs are referred to in Garmin navigators as transitions. The biggest gotcha in the GTN is that if you forget to choose an IAF or transition, it defaults to vectors. This is much better handled in the GNS, where you're prompted for the IAF. Remember when you load the procedure to check the waypoints, tracks and distances against the plate. This should be done on the approach page, because if you do it on the flight plan page, the distances will be slightly different because of flyby waypoints. When you're cleared for the approach, remember also to either activate the approach or route direct to the cleared initial approach fix. Activating the approach simply means take me direct to the IAF, which is also the meaning of cleared for the approach, so it's a good idea to associate the two in your mind. In newer navigators and software versions, you're given the altitude for each leg of the approach, but in older setups, you need to read them off the plate. But in either case, it's the plate that's definitive, not the database. And the database will not give you your minima. You must get them off the plate. If you have the technology to enter the decision altitude into your panel and get a call out, enter it as you brief the approach. This is easier on some panels, such as the Aspen, than on others, such as the G500 and G1000, but you should definitely do it. I've seen too many pilots getting fixated on the approach and missing the decision. When on the final approach, and definitely before descending at the final approach fix, check the annunciation. If it doesn't read the type of approach you are expecting, make sure you understand why. If you don't, execute a missed approach, go away and think about it. If you see a degraded approach, for example, LPV degraded to LNAV, make sure that you are above 1,000 feet, have the LNAV minima, check altitudes, and rate of descent to hand. The other things to check before you start the descent are the CDI selection is correct. If on an RMP approach, the line ahead is magenta. If on an ILS, it's identified either orally or automatically. The CDI is centered. The distance to run is correct. The altitude is correct. The to flag is showing. No other flags or messages are showing. Fly the final approach as I taught in the final approach video, regardless of whether it's an ILS, locator, RMP with or without vertical guidance. They're all flown the same. If you have an altitude window, enter the missed approach altitude into that early on the final approach, as soon as you no longer need the platform altitude. Keep the annunciator in your scan. If it changes to a lesser approach above the height of 1,000 feet, you may fly that approach, but below 1,000 feet, you must go around, and you can then choose to start again using the new minima. On an RMP approach, the missed approach point is normally at the threshold. That means that if you go around at 400 feet height, you are 1.33 miles from the missed approach point, maybe a minute's flight. Even from 200 feet, it could be 30 seconds. So do not expect to enter the missed approach procedure immediately. In any event, you must not start the missed approach before the missed approach point. There are places, such as Innsbruck, where doing so will take you into a mountainside. Almost all missed approach procedures have a straight ahead climb to an initial altitude. That's handled in newer navigators using what's called a fixed to altitude leg. But older boxes, such as the GNS 430, do not have that capability and may direct you into the first turn before you reach the altitude. This is potentially dangerous, and if you have such a unit, you must take responsibility for that straight ahead climb to altitude before following the missed approach procedure. So, if you go around, you must climb straight ahead to the missed approach point, when the navigator will go into suspend mode. On some navigators, such as the GTN, there is a big unmissable message on the screen. On others, such as the GNS, all that happens is that the rather tiny susp annunciator lights up, which is easily missed. So you need to be alert to pressing it. If you've been on an ILS, locator or VOR approach, you must also select GPS as the CDI mode. Finally, let's talk about holds. In real life, holds come before approaches. Whether they are there for air traffic sequencing, waiting for a weather improvement, or to sort out a technical problem, you generally fly the hold, then the approach. But when you enter a holding fix, as I said before, the waypoint sequencing is suspended. Thus, you would never continue the flight. For that reason, the hold is always placed at the end of the approach sequence, after the missed approach. If you need to fly the hold before the approach, you need to scroll down the flight plan to the very end, select the hold, and press direct. Most navigators will calculate and fly the correct join, even correcting for wind if you have an air data computer, and continue to fly the hold until told otherwise. Not all holds are coded in the flight plan, including not only en route holds, but some that are just plain missing. I've no idea how the gnomes at Jefferson Grotto choose to omit the holds they do, but if the one you want is missing, newer navigators have a mechanism to hold at a waypoint, where you enter the details of the hold and the navigator will automatically hold, again using the correct join. I've been going on far too long and will stop there. It's a big subject and no one can know and understand it all, least of all the regulators, sadly. But I've tried to extract what I think are the key points. All these points and much more are expanded in the PBN manual, freely available from the PPLIR Europe website. I hope you found it useful. See you in the next video.